Hello everyone. In this video I'm going to try to make sense out of problems 6, 7, and 10 in section 310 on Achieve for you. The first problem here, number 6, not bad at all. You're told that you have the scenario where you have a ladder and they label it A in the drawing, but they tell you that A is of length 6 meters, and we know that that's not going to change in the problem. The ladder isn't going to suddenly change lengths, but what is changing lengths in the problem is the distance that the ladder is up on the wall that it's leaning on. If you know that it's sliding away from the wall, and it told us in the problem that the ladder slides away from the wall at a rate of 0.8 meters per second. So I know in this case, and actually it's not sliding away, it's sliding down wall. That's why I have that labeled as dH dt is going to be the negative 0.8. Please understand why I put a negative 0.8 there, because it's saying if it's sliding down the wall, then you know at that point in time h is decreasing. Anytime a variable decreases, its derivative must be negative. A lot of people would make the mistake and label dH dt as a 0.8 because that's how it's stated in the problem. But if it's sliding down, it has to be a negative 0.8. Labeling that a positive 0.8 would mean that the height is increasing its distance on the wall. Now, at the point in time that we're interested in is 3.2. And the goal of the problem is to find out how fast the ladder is moving away from the wall at the instant that the height is 3.2 and it's sliding down the wall by 0.8 meters per second. Okay, so I know I can set up a Pythagorean theorem here. The sum of the squares of the bases should equal the hypotenuse squared, so x squared plus h squared is equal to a squared. So now, if I solve for x in this case, x squared plus 3.2 squared is 6 squared. I found out 3.2 squared was 10.24. Of course, 6 squared is 36. So x squared is going to equal 36 minus 10.24, or 25.76. I went ahead and said x is the square root of 25.76. Now, I'm going to use that same Pythagorean theorem, but instead of being able to plug in some variables, like the h is 3.2 and the a is 6, I can't plug them in this case until I take the derivative. Anything that varies must have a variable. Well, you'll notice down here I did go ahead and plug in something for the a in this case. I said, well, a is just 6 squared. Why? Because just like I started off the problem saying, the length of that ladder is not changing in this problem. There's no reason to even call it a variable. We could have just put a 6 there. The only reason I have an A labeled there is because that's how the problem was drawn out on Achieve. But that is not varying. Now, if you labeled that a square and took the derivative, you get 2a dA dt on the right-hand side. And you would just need to understand that dA dt is 0 because the length of the ladder is not changing with respect to time. No matter what you do, you need a 0 on the right-hand side when you take the derivative. When I take the derivative of the left-hand side, I'll get 2x dx dt plus 2h dH dt. Remember, both the horizontal distance and the vertical distance are functions of time. So you can't say dx dt is 0, you can't say dH dt is 0. We don't know what they are, or at least we don't know what dx dt is. We do know what dH dt is. So you'll notice I'll take what I know dH dt is equal to and I'll plug it in the next step. So after you take the derivatives, you plug in what you know. From this step to this step, I went ahead and just divided both sides by 2, so I didn't have to worry about them. So I just said x, which I knew was this, times dx dt, which is what I'm solving for, plus h, which was given, 3.2, times dH dt, that was also given, but I had to understand it's a negative 0.8, and I set that equal to 0. Well, I moved the 3.2 times 8 to the right, it becomes positive. Divide by the coefficient of dx dt, and so I can say this gives me an exact expression for dx dt. You just go to your calculator and you can say that dx dt is going to be approximately 0.504, and units in this problem were in meters and seconds, so it's 0.504 meters per second. So if the top of the ladder is sliding down the wall at a rate of 0.8 meters per second, then at the instant when the height is 3.2, the base is going away from the wall at a rate of 0.504 meters per second. Absolutely cool problem. Now, number 7 is similar, but there's an added step to it. So again, they give us a ladder problem, but the trick here is they give us some initial conditions at time t equals 0, but we're not interested in the rate of change at t equals 0. We're interested in the rate of change 2 seconds later. So what we're told in this problem is that we have a 4-meter ladder that's initially 1.6 meters away from the wall. So initially the base of the ladder was only 1.6 meters away. But then it's sliding away from the wall at a rate of 0.4 meters per second. You're supposed to find the change in the height with respect to time at 2 seconds. So I said, well, my original horizontal displacement was 1.6 meters. But I need to know what's going on 2 seconds later. And I know it says that it's sliding away from the wall at 0.4 meters per second. So the x, which is the horizontal position at the point of interest, is going to be your original horizontal position 1.6 plus your wanting 2 seconds later, so distance equals rate times time. Time is 2 seconds. The rate is 0.4 meters per second. This is going to be 1.6 plus 0.8. I'm getting 2.4 meters there. So I have a 4-meter ladder that's at the point of interest 2.4 meters away from the wall. And it's going to continue to move away from the wall at a rate of 0.4 meters per second. Once I have my initial triangle set up, it becomes just like the last problem. So the only added thing to number 7 versus number 6 is you had to solve for the length that horizontal base was away from the wall using the information in the problem. So now once I know that the base is 2.4 meters away, then I can use the Pythagorean theorem and say 2.4 squared plus h squared is 4 squared. So h squared would equal 16 minus 2.4 squared, which gives me 10.24. I go ahead and say the height is the square root of 10.24. Now I'm supposed to find, the goal of this problem is to find out how fast, and I know it has to be negative because if the base moves away, then the ladder is falling down the wall, height is decreasing. So I'm supposed to find the rate of how much that height, the ladder is decreasing on the wall is. I go back to my Pythagorean theorem. Again, anything that's a constant, I go ahead and just put in the number. The ladder's length is not changing, so I put in a number. Both the horizontal and vertical position of the ladder is changing, so I have to have variables there. Now I take the derivative. Derivative of x squared is 2x times the derivative of x with respect to t. Derivative of h squared, 2h, times the derivative of h with respect to t. The derivative of the ladder, it's not changing in length, thus it has a 0 derivative. Now I plug in what I know. Once you take the derivative, then and only then can you plug in what you know. Just like in the last problem, I said, why don't we just go ahead and divide both sides by 2? So I did that. Now x, that was 2.4 in our problem, times dx dt, that's my 0.4 meters per second, plus the h, well, the h in the problem is the square root of 10.24 times dh dt. That's what I'm looking for. So now in order to solve for dh dt, I just move these two terms over to the right. When you change sides, you change signs, divided by the coefficient of dh dt. That would be my exact answer, and actually this makes a nice answer anyway. So it ended up being exactly negative 0.3 meters per second for my final answer there. And you say, hey, that's not bad at all. So we know that when the ladder is moving away from the wall by 0.4 meters per second, when the base is 2.4 meters away from the wall, that's telling you that the ladder is falling down the wall at a rate of 0.3 meters per second. Okay, next problem, number 10 here. Number 10, to explain what the problem said here, it said that you have a plane flying over a station, and the plane is flying over the station at a rate of 500 kilometers per hour. Now, you're trying to find out how much the distance between the plane and the station is increasing after 1/2 of an hour. So what I did, and what the book asked us to do here, or what Achieve asked us to do, is it said to label the distance between the station and the plane at the point of interest as h. Well, first of all, and it said that the plane was flying at an altitude of 5 kilometers, so that's where this came from. Now I had to find out how far past the station did it go. And it said it flew over a station, and you're trying to find out how far the distance is changing a half an hour later. So I already know it's a distance away, and I know that that distance x is just going to be distance is equal to rate times time, rate times time. 500 kilometers per hour times 1/2 of an hour tells me, well, it's 250 kilometers past the station at that point. So I was given in the problem that it was flying 5 kilometers high. It's easy to find out the distance between the plane at the point of interest and the station. Just, again, Pythagorean theorem. 5 squared plus 250 squared would equal h squared. So h is just equal to the square root of 62,525. And I would leave that exact for my calculations. Now I have my h value. I'm going to use that exact same Pythagorean theorem to try to find out how fast h is changing. Again, remember, before you take the derivative, you need to remember anything that varies must have a variable. Well, the horizontal change is varying because the plane is going to continue to fly at 500 kilometers per hour. We know dx dt is 500 in this case. We know h is going to continue to change because as that plane continues to fly in that direction, the distance between the plane and the station will change. That varies. However, the altitude is not varying. So you'll notice I plugged 5 squared in there. I left x and h as variables. Now I take the derivative. 2x dx dt, derivative of any constant 0, equals 2h dh dt. Now it's just a matter of plugging in what we know, and just as I did in the previous two cases, I'm just going to cancel out 2 on each side, divide both sides by 2, then plug in what we know. X is 250. The rate of change of x, it's increasing its position by 500 kilometers per hour, so dx dt is 500. That's going to equal h, which we solved out up here, times dh dt. So dh dt is just the product of what I had on the left-hand side divided by the square root of 62,525. And when I did that, I got an approximate answer of 499.9 kilometers per hour. Hope this helps you out with these problems. This related rate stuff is absolutely cool, but sometimes it takes students a little bit of time to get used to it. So please let me know if you have any questions. I'll be glad to help out.